oftentimes in mathematics, we always ask, well, when are we ever going to use this? And in all honesty, for those of you, I mean, there are a lot more of you probably going to go into the business field than into the mathematics field. So this section right here is going to be way more relevant for most of you. And all of us definitely need to understand a little bit about economics, so as consumers in our market. So this pertains to everybody. So hopefully you'll see why and when you would use all of the stuff we've been doing as we apply it to what we call business calculus. Now you might actually take a course called business calculus instead of Calc 1 or Calc 2 at a college. It'd be tailored specifically to those people that are interested in a degree in some sort of business field or an MBA. All right, so looking at this, we have a cost function, and we've already discussed that. We've also already discussed the marginal cost function. So these are two things that we've already seen before in previous chapters. But we have not talked about average cost. And it makes sense that to find an average, we just add everything up and divide by the number we have. That's exactly what's happening here. We take the cost, the whole cost, divided by how many pieces we have to get the average cost. All right, so our new item of business, so to speak, would be our marginal or our minimum average cost. So we've already dealt with marginal cost, and marginal cost is just the derivative of the cost function. I guess I will also quickly throw in, you'll see this in my notes and in my homework. This is my lowercase c, it's kind of a cursive lowercase c, and then this is my uppercase c. When I'm talking about the lowercase c, I'm referring to average cost. When I have the uppercase c, I'm referring to marginal cost, or the cost function in general. All right, so minimum average cost is just a formula. And if you notice, the formula just says when the marginal cost equals the average cost. So, in other words, where capital C prime of x equals lower c of x. Another way to look at this is when the derivative of a function equals the function divided by x. Because as we can see up here, that's exactly what c of x is, the average cost. All right, so let's see how this works. Let's go to an example. All right, so for our first example, we have a company that's just producing so many items, and we have this cost function that has been derived. Now, later on, we will actually derive the cost functions, but for now, we're just going to start with one and see how we use them. So we have this cost function, and we're asked in A to find the cost, the average cost, and marginal cost of producing 1,000 items. Well, the regular cost is just going to be plugging 1,000 in to the original equation. So if I just plug that into 2,600 plus 2 times 1,000 plus 0.001 times 1,000 squared, I end up with 5,600. So that's how much it would cost to produce 1,000 items of this commodity. All right, then average cost is simply going to be what we just got. So this 5,600, and we're going to go ahead and divide it by 1,000 because that would be how many items we found the total cost for. So the cost per item, the average cost per item, is about $5.60 per unit. All right, and then we're asked to find the marginal cost. So first I'm going to go ahead and find the derivative. And the derivative in this case is going to be 2 plus 0.002x. And now I'm going to go ahead and plug into that the 1,000. And when I do that, I get $4 per unit. So our marginal cost is actually less than the average cost. And if you think about what that would tell us, we've talked about that our marginal cost actually predicts the next item. So that predicts the cost of the 1,001th item. So this is about what it would cost, but we're saying it's about $5.60 per unit. So obviously we have not maximized this process yet. We're not quite there. They're not close enough. So we're going to go ahead and see at what production level the average cost be lowest and what the minimum cost would be. So looking at this, we're going to go ahead and use our formula, and we're going to set our C of x equal to our C prime of x. All right, so when we look at that, we end up with our C of x was... All right, I apologize for my son interrupting. Okay, so let's take a look at this again. Small c of x would be 2600 plus 2x plus 0.001x squared, all divided by x. That's the average cost. And we're going to set that equal to our derivative, which we found, which was 2 plus 0.002x. Now we're going to solve it. And something that you will notice, that I always notice in this anyway, is that really, another way to look at this formula is that it's the original cost function equal to the derivative times an x. So, that's what we would get right here anyway. If we go ahead and multiply both sides by x, the left side we just get back to the original cost function. And the right side we get the derivative times x. I'm going to go ahead and distribute that x while I'm at it. All right, I would like you to notice that there is a 2x on both sides, so I'm going to reduce that. And then I'm going to go ahead and move all the x squareds to one side. And I have the 2600, so I will have 0.001x squared when I go ahead and subtract this from both sides. And if I divide that out, I get x to be about 1,612. So at about 1,612 items, we're going to have our minimum cost. And now the question was, what was that minimum cost? Well, that minimum cost would simply be plugging in the 1,612 items to the average cost, because we want to know per item what would that be, and the average cost per item at that point would be $5.22. And again, I plugged that into the average cost. So $5.22 per item. All right, so that's just one example of the ways that we can use this. All right, so now that we've gone through cost, obviously we don't want to have to pay out money, or if we do, we want to take in enough money that we make a profit. That's the whole point of business. And so we're going to get into the demand side. Oftentimes in economics we refer to it as the demand function, or supply and demand, but in calculus a synonym for that would also be a price function. So what do we charge per item? So we have the price function we're just going to represent as P of X. All right, and that's just price per unit. And that's how much we're going to charge per unit. So it makes sense that the revenue, or how much money we take in, and again, revenue would be more of an economic term, sales function can also be synonymous with that. But basically for revenue, we want to know how much money we're going to take in. Well, if I sell one item, I take in 1 P of X. If I sell 5 items, I take in 5 P of X's. So in other words, however many items I sell times how much I'm charging per item gets me my revenue. So this is the formula for revenue. Now the nice thing is, every time you see the word marginal, it means derivative. So marginal is always the rate of change. And so this is really just revenue's derivative with respect to X. Jumping down here to marginal profit, we have the same idea. It is just the profit's derivative. However, we haven't talked yet about what profit is. And of course, profit is the money we have left over after we take in a bunch of money and we pay out all of our expenses. So it makes sense that profit is found by taking all of our revenue, or what we take in, minusing how much we had to pay out. What did this cost us? And then that's our profit, what's left. And again, that's the whole premise behind business. Like we want to make a profit. Some people, unfortunately, are willing to do things that aren't necessarily good just to make that profit. So we also want to make an ethical profit, and keep that in mind if you're going into the business world. And of course, along with ethics, we do want to maximize our profits ethically. And one of the ways that we can do that is we can set our marginal, we can find the maximum profit by setting our marginal revenue equal to our marginal cost. So remember, marginal means derivative. So this happens to be two derivatives being set equal to each other. So whatever we take in, its derivative equal to the derivative of the cost. If the slopes are the same, then we're going to have a maximum profit. All right, so I have two more examples here for you over this business calculus stuff, and then you'll have several problems to practice on homework. But for this one, we're supposed to determine the production level that will maximize profit. So this is going with what we just did. We want to maximize the profit. And so again, that formula to have maximum profit is R prime equal to C prime. So we first need to make sure we have a C and we have an R so that we can take their derivatives. I notice right off the bat, I do have a cost function. So I have the C, so I can find C prime. But what I notice I'm lacking, I don't see a revenue function. I do, however, have a demand function. So I know if I'm charging, if this is this one here in the blue is my price per item, well, to figure out how much money I take in, I just need to take that price per item times an X. So in other words, to find the revenue function, since I wasn't given that one, I do have to develop it or derive it, and I simply just multiply the demand function times an X. So it'll be 3.5x minus 0.01x squared. All right, now that I have my revenue and I have my cost, I can go ahead and take their derivatives and set them equal to each other. So the derivative of the revenue function is going to be 3.5 minus 0.02x. I'm going to set that equal to the derivative of the cost function, which would be 1.26 minus 0.02x plus 0.00021x squared. And, you know, on one of our tests, a lot of people had an extra zero in here, but you have to realize that when you multiply that out, the place value stays the same. So really, instead of 7, it becomes 21, but its ending place value is still going to be in the same location. Okay, we now need to solve this. So I notice we can get rid of that because I'm minusing a 0.02x on both sides. And then I'm just going to do some shifting around here. If I move things around and combine like terms, I'm going to end up with 2.24 on this side if I subtract off that 1.26 from both sides. And then I still have my 0.00021x squared, and I'm going to go ahead and divide that out. And when I do, and I let the calculator do the work for me, I got 10,666 and 2/3 for my x squared. Again, I let the calculator do the work for me, and I get about 103. And remember, we're producing an item, so it would make sense to have whole items produced. So it's okay to round it to the nearest whole number in this case. Now, depending on what type of business calculus you're in, you may take it out a few decimal spots. But for our purposes, whole number items is fine. So we know that at 103, that is our production level that will maximize our profit. All right, so for our last example, we are going to look at getting new uniforms for the BHS basketball team, both boys and girls. And we find that the average basketball attendance for the games is about 400 fans when the tickets are set at $5. But when we lower the ticket price to $4 per patron, the average basketball attendance rises to 550 fans. And so we haven't done this yet, but we can actually write our own demand function based off of this. So we can look at how are these two things related if we assume that there's a linear relationship going on. Now, I realize that there might be exponential relationships and whatnot, but we're going to assume there's a linear relationship in this case. So we have a linear relationship, and basically I'm picking out 2 points in this problem. I see 405, and then I see 550 and 4. All right, so a common misconception here is to not know how to set up your points. So we have these 2 points. We have x and y values. And if we think about it, we're going to make a demand function. So it's going to be P of x equals. So we're going to figure out how much we're going to charge per person. So in looking at this, our output values are the prices that we're charging. So in other words, our outputs or our Y values are going to be the $4 and the $5. And our input values are going to be our $550 that went with the 4 and the $400 that go with the 5. So that's how I know how to set up my points, because I know that the price function's output has to be, or our demand function has to be in dollars. That label has to be in dollars. Okay, so if we assume this was a linear relationship, let's review really quickly that we have this new equation, point slope, that we are liking to use here in calculus. And if I do that, the first thing I need to do is find the slope. So the slope of this happens to be, if I go ahead and subtract my y's, subtract my corresponding x's, and reduce, I get -1 over 150 for the slope. Doesn't matter which point you pick. I'm going to go ahead here. I need to make a subtraction sign there, sorry, instead. So y minus, I'm going to use the point 400, 5. So y minus 5 is going to equal -1 over 150 times x minus 400. All right, so that is my equation. However, since this time I do want this to be in the form of p of x, I am going to go ahead and solve this for y, get y all by itself. So if I do that, I get -x over 150 plus 7 2/3. And you can verify that if you want with your calculator or do the math. I'm not going to show all that math on here, so I know you guys are fully capable of doing it. So our demand function will be this function right here. All right, so now that we have a demand function, we are asked to figure out how to maximize, what should we put the ticket price at in order to maximize revenue. So in other words, if it's too high, not enough people come. If it's too low, a lot of people come, but I can actually make a little more money if I would raise the price just a little bit. So what's that magic number? What should the price be at? Or if I lower the price a little bit, I can go either way. I can get more people. So looking at this, if I just want to maximize revenue, we're not dealing with cost in this case at this point. We're just dealing with maximizing the revenue. So I just need to find r of x, and I'm going to figure out where that is equal to 0, so I can find that maximum value. Sorry, r prime of x is equal to 0. But our first thing we have to do is find r of x. So to review, to find r of x, we just take the demand function times x. Well, we just wrote a demand function in letter A. So I'm going to go ahead and take that demand function times x, which will give me -x squared over 150 plus 7 2/3 x. Now I'm going to go ahead and do the derivative to get the marginal revenue so that I can set that equal to 0 and figure out what I should have. So the marginal revenue is going to be -x over 75 plus 7 2/3. If I set that equal to 0 and solve, and again, I'm not going to go through the solving, but you can add -x over 75 to both sides, and then multiply by the 75, you end up getting x equals 575. So we can get an attendance of 575 patrons to the game if we set the ticket price at, and now we're going to plug that into the demand function to figure out what should the ticket price be. So I'm going to go ahead and plug this into the original demand function. So it'll be -575 over 150 plus 7 2/3, and that is about $3.83 per seat. Now, if you're in the business world, does that seem realistic? Are you really going to charge $3.83 per seat? Because now you've got someone who's running a cash register or who's taking the money, and they need other tools in order to be able to count back the change, because this isn't a nice number to work with when you're speaking of money. So this really doesn't make sense to set it at $3.83. And so that's where sometimes we have to use our common sense in the business world. The mathematics will help us get there, but sometimes we have to make a decision. So I don't know what you want the decision to be on this one. I'll let you decide that. And if you want to come in and chat with it about me, I would love to do that. All right, good luck on your homework.